we were talking about free modules last time. So, a module an A module M is a free module if M is equal to direct sum of Mi I in some indexing set I with Mi isomorphic to A for all I in I. Okay. So, we know that, see, if you take a vector space V, finite dimensional vector space, then we know this is isomorphic to Fn. V is a finite dimensional vector space over a field F, then V is isomorphic to Fn, where n is the dimension of V. Now, I take a module M. M is an A module. Okay. What is meant by this being finitely generated? M is finitely generated if I can find some M1 up to Mn such that M is equal to summation Ai Mi I from 1 to n Ai belong to A. You can write every element of M as a linear combination like this. Of course, we have already seen that one does not have analogues of basis, right. We need not have any finitely any generating set need not be reduced to a linearly independent finitely generating set. So, we might not be able to expect something like this, but still looking at this, can you think of some linear maps or homomorphisms from where to where? From, so here we could think, given a basis V1 up to Vn, we usually define a map from Fn to here, right, Ei the standard basis being mapped to this basis. So, here again similarly one can think of a map from An to M, right, Ei being mapped to Mi, or in other words, if you take any n tuple, this is being mapped to A1 M1 plus etc. An Mn. This is a homomorphism. Okay. Define phi from An to M by, or phi of any A1 up to An is A1 M1 plus etc. An Mn. This is again inspired by the definition of linear transformation in the case of vector spaces in a similar situation. But now, so what we have obtained is that homomorphism and A module. Okay, so this is check that phi is is an A module homomorphism. What more can we say about this homomorphism? This is onto and phi is surjective. Is this injective? Need not necessarily be injective, right? For example, if you take map from Z to Zn, I mean Z5, this is a finitely generated Z module. A generator of this is 1, okay. 2, any one of them is a generator here, but so if you take 1 going to 1 bar, then there is a kernel here. Kernel phi is, what is kernel phi here? 5z, right? This is Z mod 5z. This is a natural map from A to A mod I. The kernel of the natural map from A to A mod I is I. Kernel is I. So therefore this has a kernel. So this in general need not be injective. But what we can say is that there exists, if M is finitely generated, there exists an A module homomorphism from An to M, a finitely generated free module. This is a finitely generated free module, and there exists a onto homomorphism from An to M. Suppose conversely, suppose there exists a finitely generated free A module, say F, okay, and an A module homomorphism phi from F to M, which is onto what can you say about M? M has to be finitely generated. In fact, you can very specifically mention what get a finite generating set, right. So let F be isomorphic to A power n, okay, then and let, so this is isomorphic via psi, and let Fi be psi I of Ei, then and Mi be equal to phi of psi of Ei and phi of Fi, then M1 up to Mn is a generating set for M. So what we have proved now is let M be an A module, then M is finitely generated, if and only if there exists a finitely generated free A module F and a surjective homomorphism phi from F to. For the converse part, we do not need the free condition here. If I have a finitely generated module M, finitely generated module F and a surjective homomorphism, then M is also finitely generated. Now, finitely generated modules are very special, they behave very well, I mean as in the case of finite dimensional vector spaces, particularly when the ring is also nice, which we will see later when the ring is Noetherian. So, first of all let us look at one important property of modules, finitely generated A modules. So, let me state the result. Let M be a finitely generated A module I be an ideal of A and phi be an A module homomorphism such that phi of M is contained in I M. Okay. Phi of M is contained in I M. What does this mean? Say for example, if I have Z to Z, M going to some K M, fixing a K, this is a Z module homomorphism, and this, if I call this phi, then phi of Z is contained in Kz. So, if you take I to be the ideal generated by K, then this is phi Z is contained in, phi of M is contained in I M. That is the condition that we are looking at here. Okay. Suppose there exists an ideal I with this property, then there exists A naught A1 up to AN in I such that phi power n plus A1 phi power n minus 1 AN minus 1 phi plus AN is 0. So, this is as a as an element in no, what is phi? Phi is a homomorphism. So, what is meant by phi square? What is phi square? Exactly. So, this as an element in hom A M M, this has another name called set of all endomorphisms of M. As an element of the endomorphism, this, see, we have seen that hom for any modules M and N, hom A M comma N is a module, A module. If if I look at this hom M M, this has a natural multiplication. What is that? the composition. If I take F and G, F times G is their composition. That is again a homomorphism, that will again be an endomorphism of M. But now this ring is not commutative. F times G is not equal to G times F, but this is indeed a ring with respect to the addition and multiplication. This is indeed a ring. Now what this says is that I can, I get a linear combination of identity phi square up to phi power n in the endomorphism ring whose linear combination is a 0 map. Okay. Does this look somewhat familiar? Put this in the situation of in the vector spaces, or does this look somewhat familiar?
Yeah, I have a question.
Yes.
In the previous proposition, you said that for the converse by Frey model is not needed.
Yeah.
But then we use the fact that F is isomorphic to A and.
So if I have a what we have ultimately done here, we have taken a generating set of this module, okay, and mapped to corresponding generating mapped to the corresponding generating set in M. Okay. So here if I have a generating set, let it be some module f1 up to f m. Suppose this is a generating set, then every element is a linear combination of linear combination of the form AI Fi. Now look at I am sending Fi to, look at the images of Fi. Then if I take any element here in M, look at the pre-image of that will be some AI Fi. So therefore phi of that will be sigma AI Mi. So therefore this every element in M is a linear combination of M1 up to Mn. Therefore it is finitely generated. Okay, so let us try to prove this. So here M is contained in phi of M is contained in Im. M is finitely generated. So let us start with the generating set. X1 up to xn be a generating set for M. Therefore I can write phi of xi, this is equal to summation j from 1 to n aij xj. And where are these aij's coming from? Phi of xi is contained in Im. Every element of Im looks like summation some aij, alpha ij yj, where alpha ij come from I and yj come from M. But every element of M is a linear combination of x1 up to xn. So each yj I can expand and then write it in this form ultimately. So this can be written, I collect all these expressions and write this as phi delta ij minus summation j from 1 to n aij xj. This is summation is 0, right. Now look at this. This is again, consider phi delta ij minus aij. So I am writing this as a summation outside this, I am sorry. So this should be here, j from 1 to n. Consider the elements phi delta ij minus aij. I mean delta ij is the Kroneker's delta. I mean it is 0 if I is not equal to j and is 1 if I is equal to j, or in other words here phi will be, I mean in this summation when j runs from 1 to n, this will be non-zero only when x j is I. So phi xi will come from this part, and from this part the whole thing will come. Okay. So I have just written a compact form. So look at this. This is an element of, so you can think of this as aij times identity, or else you can think of aij as the constant multiplication map from m to m. Aij can be thought of as the homomorphism sending x to aij times x. So you can think of this as an element in a prime phi. What is a prime phi? Where a prime phi is the subring of the endomorphism ring containing a prime. This is image of A in and phi. That is, I consider the smallest subring containing all these constant maps, constant multiplication maps, and the homomorphism phi. So every element in phi looks like summation ai phi power I from 0 to n, n in n, ai in a. This is what my, I mean I am denoting it a prime because it is not really a. It need not necessarily be even isomorphic to a, because the multiplication map can be 0. If you take a, if your module M has an annihilator, and if you take an element from the annihilator, multiplication by that would be 0. So therefore that in this ring, that element will be, everything in the annihilator is same as 0. So that is why I am denoting it by a different notation. A prime phi, this is a subring of endomorphism. Okay, it is not clear to you. Do you understand this notation? So this is the collection of all elements of this form. One can.
So how this include image of A in endomorphism?
That is what I said. See, every element AI is a multiplication map, right, from M to M is the map AI of X is AIX. So every constant can be seen as the constant multiplication map, okay, multiplication by that constant. So that way I have a image of A inside endomorphism. Okay. Now our ring endomorphism of A end M, this is not a commutative ring, right. In most cases, in the general case, this is not commutative. What can you say about this ring? What can you say about this ring? Take any two elements, F and G.
Because AI are from commutative ring and phi commutes.
Phi always commutes, right? Phi n composition phi m is same as phi m composite phi n. So therefore, this is a commutative subring of Now we will have to talk about a theorem, that is, you have seen in the case of vector spaces over fields, and I will take the freedom to ask you to go through the proof again and see that the theorem is true for modules over commutative rings. Okay. That is, or it is over commutative rings, there is no module involved here. So it is basically the Cayley-Hamilton theorem. What does Cayley-Hamilton theorem say? The Cayley-Hamilton theorem says that if I take a matrix A in M and F and look at determinant of, so I write P x as determinant of A minus x I or x I minus A, either way. If P x is this, then P A is 0. So here we are looking at elements, matrices A with entries coming from the field. Okay. Now how do you prove this? What you do is look at this, take this matrix, multiply, look at this matrix containing the cofactors, basically the adjoint, and then multiply and see that this gives you the determinant and that gives you the the 0. So if you look at the proof does not use anything that this is the ring or the elements need to have a multiplicative inverse. What is needed is commutativity. You need to multiply elements, switch them accordingly. See, when you take the determinant and expand, for that you need commutativity. So the only assumption needed for this statement to be true is commutative ring. Ring should be commutative. So here I am, if I replace this by a commutative ring R, the statement is still true. Now let us come back to this. These are all elements in a commutative ring, and I look at this matrix the matrix consider the matrix let me call it B to be equal to phi delta ij minus aij. So, aij as I said thought of as the multiplication map. This is an n by n matrix in with entries coming from A prime phi matrix over a commutative ring. Okay. Now, let Bik denote the cofactors of B, that is Bik is the determinant of the matrix obtained by removing the ith row and kth column. Okay. And we are just proceeding in the manner that one proves the Cayley-Hamilton theorem. There is nothing more to it. So, now, so I have this system of linear equations I from 1 to n phi delta ij minus aij xj is 0, sorry, j from 1 to n. Okay. If I look at this, so I take this cofactors. If I take Bik phi ij phi delta ij aij j from 1 to n and take the summation over all I, this will turn out to be equal to the determinant. So, this will be, so this acting on any xj is 0 and that will say that, so this if you expand, what you get is the determinant of B acting on xj is 0 for all j, and that would imply that determinant of B as a function in, as an element in A prime phi is 0. This is the 0 map as an element of but what is determinant phi? If you expand this, what you get is a degree n equation here, okay. I mean phi power n. Now, look at each aij come from the ideal I, from the not only from the ring, because you know phi of m is contained in I m. So, therefore, each aij come from I. Now, look at the expansion of determinant of B. Determinant of B, look at the highest power, that will be phi power n, and then so this your matrix looks like this. Phi A11 phi minus A11 minus A12 minus A1n, A21 minus A21 phi minus A22 minus A2n minus AN1 minus AN2 phi minus AN. Right, this is how the matrix B look like. Determinant of B will be again an element of A prime phi, and as an endomorphism from M to M it is 0. But what is determinant of phi, determinant of B? It will be this times determinant of this plus determinant of the rest and so on. But that will be again some phi power n plus the coefficient of phi power n minus 1 will have some aij's, some linear combination of aij's. So, this will be a1 phi power n minus 1 a n minus 1 phi plus a n right. Each ai, see they are all coming from here, all these ai's are linear combinations of some linear or combinations of all these aij's, they are all in I, the ideal I. So, ai belongs to I, and that is precisely what we were trying to prove. Okay. So, here in the proof there are only two things that we have used. We have not really used the Cayley-Hamilton theorem. One can use Cayley-Hamilton theorem and get this. What we have done is we have just gone through the proof of Cayley-Hamilton theorem. We take B, take the cofactors, multiply with the cofactors, correct cofactors and sum it over all of them. What you get is determinant. And this applied on xj is 0 implies the determinant applied on xj is 0 for all j. That is precisely, as an element of or as a map from M to M it is 0, and determinant of B, once you express it in this form, what you get is the required form. Okay. In the statement of the proposition, we have mentioned ai belong to I, but one can see that it is not only this, it is little more. One can see that ai belong to in fact I power I. See, if you look at coefficient of phi power n minus 1, it will be some n minus 1 product times one aij coming from here. Okay. So, therefore, that aij will come from I. So, a1 belongs to I. Now, let us look at phi power n minus 2. Phi power n minus 2 will be, there will be phi power n, n minus 2 of them, and then there will be several power of phi power n minus 2 you get in several ways, not only one way. But in all these ways you will have n minus 2 of these terms involved and 2 aij products. So, each aij belongs to I, therefore, these two will give the element in I square and so on. It is basic counting in some sense. So, one can obtain that ai is in I power I. This has a very important corollary. Suppose I take, let M be a finitely generated A module and I be an ideal in A such that M is equal to I n. Okay. Then there exists an element x in A such that x minus 1 belongs to I and x m is 0, or x is in the annihilator of M. And this can also be written as x congruent to 1 mod I, or in other words, there is an element which is a unit in A mod I and annihilating M. Okay. This is straightforward from the previous theorem. If I take phi to be identity map from M to M, then what do you get? There exists A1, A2 up to AN in I such that, so there exists A1, AN in I such that phi power n, if phi is identity, phi power n is identity. So, you can write it 1 plus A1. So, you can this can be thought of as, phi can be thought of as constant multiple, like 1, constant multiple of 1, okay, 1 plus A1 up to AN. This is 0, which means this acting on M, any element in M is 0. Now, this is an element in A, and what can you say about, so this, if I take x to be equal to 1 plus A1 plus etcetera AN, what can you say about x minus 1? X minus 1 is in I, right. So, then x minus 1 belongs to I and x m is 0. So, now there is this gives one of the most important basic results in commutative algebra called Nakayama's lemma. So, in the paper of in the book of Matsumura, there is this book commutative ring theory by Hideyuki Matsumura. In that book there is something interesting written about Nakayama's lemma. It seems Nakayama claims that this is not his contribution. It is it should, I mean, according to him it should be attributed to Azumaya and Krull. So, in Nakayama's in Matsumura's book, he writes it as he writes theorem, and in bracket he writes NAK, and many places it is used like this: Nakayama, Azumaya and Krull. Okay. But we always refer to it as Nakayama's lemma. It has been like that for a while now. So, what does this theorem say? Let I be an ideal contained in Jacobson radical of A, let M be a finitely generated A module. If IM is M, then M is 0. Think of this situation in the local ring. Suppose you have a local ring, every ideal is contained in the Jacobson radical, because there is only one maximal ideal. Every ideal is contained in the Jacobson radical. So, what it says is that in a local ring, if you take a non-zero module, then IM can never be equal to M. Okay. But this is not true in general. Say for example, if you take Zn or Z5 over Z, can you think of an ideal I such that Z5 is Z5? If you take 5Z, then it will be 0, right? I take M to be this and A to be Z. Now my question is, can you tell me an ideal I such that IM is equal to M? Three Z. Will this be satisfied? Yeah? 3? 3 is a generator in M. So what? One can, so if you think of this, now this is 3 is a unit as well. So 1 will be here, right? 1 will be in IM. So as a module, if a submodule contains that generator, it will contain everything. Now can you generalize this? If you take Zn, can you give me an ideal I such that IM is M? You take any I equal to mz, where m is co-prime to n, then M will be equal to M. Okay. So this is not true in general. I mean, this statement, see in this case, note that all these ideals are not, if you take, this is not a local ring, but this is a commutative ring. None of these ideals are in the Jacobson radical. What is the Jacobson radical of A? Intersection of all maximal ideals. What is the Jacobson radical of A? 0, right? There cannot be any nz there. If you take any nz, you can always find a maximal ideal n which skips a maximal ideal. So intersection of all maximal ideals. So therefore this is, I mean, this is not a counterexample to the Nakayama lemma. What I am saying is, if you remove this hypothesis, this is no longer true. Okay. We will prove Nakayama lemma in the next class.